Okay, welcome back everyone. In this video, I'm just going to show you kind of quickly several things that actually result from realizing that the force of gravity is a centripetal force. And in many cases, if we ignore kind of minor forces from other planets, the force of gravity between a planet and the sun is the only centripetal force. And so that allows us to calculate several things. So I'm just going to kind of set up the equation that the force of gravity is equal to the centripetal force, and I'm going to see what happens. So we have Gmm over r squared, and just for fun I'm always going to use a capital R. So let me know if you don't see me sticking to that. The centripetal force is going to be ma, mass times centripetal acceleration. And so I can just cancel out one of these r's directly, cancel out the little m, and get that this v is the square root of gm over r. Now this is what we call the orbital speed, or orbital velocity, if you will. Okay, so I'll put a v orb on that. That's how fast you have to be moving in order to orbit. And for the Earth, I believe for the Earth it turns out to be somewhere on the order of 5 kilometers per second. So the surface of the Earth. Okay, so that's the first thing. The second thing is Kepler's third law. So we say force of gravity is centripetal force. Whoops. So Gmm over r squared equals m v squared over r, but now we remember that v is 2 pi r over t, and that was something Mr. Baker explained in a previous video. The little m still cancels out. I'm going to leave the r for just a moment. You'll see why. Gm over r squared is equal to 2 pi r over t quantity squared over r. Okay, so I continue with this. Gm over r squared is 4 pi squared r squared over r t squared. So this t right here got squared and came to the denominator. Hope you see where that happened. Okay, now I can start canceling things out. One of these r's is going to go away, and if I move my 4 pi squared to the other side, and if I move this r squared, basically if I flip those, I will get Gm over 4 pi squared is equal to r cubed over t squared. And that is what we said previously was Kepler's third law. Okay. Now, for the last thing I'm going to prove, I'm going to start with another applet. And this is kind of a nifty one. When Newton was thinking about gravity and orbits, he said, well, and I'm going to pause this so I can reposition the screen. Okay, so I've repositioned the screen, and I've also got it so that hopefully you can see the URL. So you can just search for Newtonian mountain. And actually, let me see if I can move this up a little bit more. Okay, so Newtonian mountain is what we're talking about. This was a picture that appeared in one of Newton's books long ago. So he said, alright, imagine you're standing on top of a tall mountain and you fire a cannonball. Okay, so this is 10,000 miles per hour. Well, of course, it's going to fall down to the earth. Okay, well, what happens if you fire it a little bit faster, so like 12,000? Alright, so it'll go a bit further, okay? What if instead of that you do like 14,000? Okay, I think you see the trend here. Eventually, if I get enough velocity, it's going to follow an almost circular, this one's a bit elliptical, almost circular path, and come back and hit the guy in the back of the head. Now that's ignoring air resistance and other mountains that could be in the way, but you get the idea. And so that's a representation of what we previously called orbital velocity. But now what happens if I kick it up a little bit? Now if I just kick it up a bit, alright, you can see the little object is going to come back because it kind of makes the turn. And so there it is.
Ouch.
But what if I kick it up even more? So I'll just max it out. Well, maybe not quite max it out, but a lot. Okay? And what if I try that? Well, that doesn't look so good. Okay, I'm gonna do that one more time. I don't know if you heard it. And so what that tells us is that the object has escaped from the Earth's gravitational field. Okay, so now we're going to go back to the derivation. So I'm going to pause this again and I'll show you how this works. Okay, so now let's talk about how this escape velocity really works. And what you have to think of first is, well, what would I have to do to get something to escape from the Earth? I could throw it straight up, and if I didn't throw it very fast, you know, what goes up must come down. But imagine that I was able to throw it with enough speed that it kept traveling and it escaped the Earth, ignore the sun, and I threw it fast enough so that it just barely makes it to the edge of the universe before turning around. And this is kind of a weird concept, but go with me. Okay? We can use energy to kind of predict what the speed must be. So the energy that it starts with must be equal to the energy that it ends with. And it's going to start with potential plus kinetic, and it's going to end with potential plus kinetic. Oops. Potential plus kinetic, right? Okay, now remember we said that potential energy is GMM over R with a negative. Okay, so go back and review that video if you're like, whoa, what is that? Okay, remember that this is like saying that at the edge of the universe, when R is equal to infinity, U is equal to 0. Okay, so when we're sitting on the surface of the Earth, well, R is going to be the radius of the Earth, so our starting potential is negative GMM over R, where that's the radius of the Earth. And of course the speed we throw it with gives it kinetic energy of 1/2 mv final, or v squared. Okay, now the final potential energy has to be 0 because it's just barely making it to the edge of the universe, so R is infinite. And of course, if it just barely makes it there, it's going to stop moving. So its final kinetic energy is also 0. Okay? So what this gives us is an expression where 1/2 mv squared is equal to GMM over R. And notice that again, the mass of the object cancels out. I multiply by 2 on each side, take the square root, and what I get is that the escape velocity is 2 GM over R all in the square root. Notice that this is the square root of 2 times orbital speed, which is kind of cool. Okay, and so there you have it. If you want to escape from an object that has mass m, then you use this equation. Now something for you to think about, kind of a brain teaser, is what if the escape speed was c, the speed of light? What happens if you put that in and solve for everything else? I'll let you think about that and get back to me in class.